Hello and welcome to Physics Tutorials with Lumina Collins Ono Brakwaya. You can simply call me Mr. Collins. In this video we shall be studying motion of connected bodies. Alright? Now why is this topic important to us? With this topic we will be able to understand how Newton's laws of motion or the derivative forms of those laws can be used to describe the position, the motion, and the acceleration of individual components of a system of connected bodies or of the entire system as a function of time, alright, which means we can tell the position, motion, and acceleration of each component of each body that makes up the system or of the entire system as it relates with time. Okay, now there is a sign convention we'll be making use of for our calculations. Now let us consider this sign convention. What does this mean? It means when a force moves a body towards the right, we say it is positive. But if it moves the body towards the left, we say it is negative. Also, when a force moves the body upward, then we say it is positive. And if the force moves the body downward, then we say it is negative. Okay, let me explain. Let's consider vertical forces, for instance. Now here we have a mass that is suspended by a string. Let's assume that the string is attached to a ceiling, okay, such that the weight of this mass would have pulled it downward. So the weight acts downward, and then by virtue of the tension acting here, we can write T here, which means T here stands for the tension. So there are two forces at work on this mass. One is its weight, which pulls it down, and the second is the tension, which keeps it suspended by acting upward to counter the weight. It means therefore that the net force on this body is equal to the tension, which acts upward, and then we say minus the weight. We put a minus sign there because our weight here is acting downward. Okay, and don't forget our sign convention. We said when a force acts downward, we say it is negative, and if it acts upward, we say it is positive. So we have the net force is equal to the tension, which is the upward force, minus the weight. Okay, now we can still break this down further. What is our net force? From Newton's second law of motion, we know that the net force is equal to the change in momentum of a body with respect to time. Alright? And then we also know that this change occurs in the direction of the applied force. So the force is equal to the time rate of change in momentum. Momentum is a product of mass and velocity. It implies therefore that the force is equal to the change in mass times velocity with respect to time. However, the mass is constant. Alright? For most motions that we'll be solving, the mass is constant such that the change in our momentum P is caused only by the change in velocity. For instance, if a body falls from rest, while it was at rest, its velocity was 0, but as it falls, it experiences an increase in its velocity. In all, the mass can be brought out because it's constant, and as such we have F equals m dv dt. But then the change in velocity with time is called acceleration, which means we can write F equals ma. Alright, which means therefore that our net force can also be written as ma. Alright, then our weight can also be expressed as mg, because for the weight the acceleration is caused by gravity. Okay, which means this whole expression here can then be expressed as, for F net we can write ma, and then that becomes equal to c minus, for the weight we can write mg. Okay, now when a body is moving upward, then we can write this expression. Why? Because the net force is causing the body to move upward. But if a body moves downward, for downward motion, for downward motion. Now, if the body moves downward, what do you think we should write? Minus ma, alright, equals T minus mg. Now, this is something we would see a lot when we begin to solve questions on pulleys. So let's assume we have two bodies here. This is body 1 and this is body 2 that are connected by a string such that there's a similar tension, or the tension is equal because the pulley is frictionless. Okay, now let us assume that body 2 here has a greater mass and as such a greater weight than body 1. Okay, while we consider the motion of this body 2, we can write the equation of its forces as, now since it has a greater weight, it would move downward, it would accelerate downward. So when considering the body 2, we can write minus ma equals tension minus its weight mg. Alright, that's for body 2, let's say m2. Alright, but if we're considering m1, you would know that when this body goes downward, this body 1 would go upward. Alright, so for body 1, we'll just write it as m, let's call this m1a, alright, equals t and then minus m1g. Alright, now this is for m1. Okay, now its weight would always act downward. That is why the weight always has a negative sign. Alright, but whether the whole system moves upward or downward is what informs our decision as to the sign that is applied in front of its net force. So when the body goes upward, then we can write it as m1a or generally as ma. Alright, but when the body goes downward, then we write it as minus ma. Okay, so this is the sign convention we shall be making use of during this discussion. Okay, now let us consider horizontal forces. So let's assume we have a body, okay, such that there is a force that pulls it forward. All right, now there would be a tension here, T. Alright, now the net force. Now, first of all, how many forces are acting here? There's a tension T, there is also its weight. Okay, alright, now we must consider the fact that it is not, the table is not falling, the table is not caving in. Okay, it means therefore that there is another force that balances the weight or that cancels out the weight. Okay, so the weight should have made the table to cave in, but it isn't doing that. Now, why? There is an upward force which we call the normal reaction N. Okay, and then there is frictional force. If the surface, if there is friction between the body and the surface, then there would be frictional force acting backward. Alright, now let us take the first case, the case where there is no friction. It means we can write that the net force F net equals just the tension. Why? The normal reaction cancels out the weight, so there is no net vertical force. Alright, the only forces we have here are horizontal, and for the first one we're studying a case where there is no frictional force. As such, the only force that we would have left is the tension, which means therefore that the net force is equal to the tension, or we can say ma equals the tension. Okay, now how about the case where we have frictional force? What happens? Now we must know that our frictional force is proportional to the normal reaction N. Okay, that is among the characteristics of frictional force. It depends on the normal reaction. Okay, now since our normal reaction balances the weight, it means it has the same magnitude as the weight. for bodies that lie on horizontal surfaces, which means we can write that our normal reaction N is equal to the weight, which in itself is equal to mg. Alright, which means therefore that we can say the frictional force is proportional to mg. Alright, as such, we can say the frictional force is equal to a constant and then mg. This constant here is called the coefficient of frictional force. Alright, now if we consider the fact that there is friction now which opposes the motion of this body, it means therefore that our net force is equal to the tension which acts forward, alright, which acts towards the right, and as such we say it is positive, and then our friction acts backward, right, and so we'd say minus our frictional force. We have said is mu mg, so we can write mu mg. Okay, which means we have MA equals tension minus mu mg. This becomes the motion that expresses all the force components that are acting on this body. Okay, now let us take a second case. A case where there are two forces pulling the body horizontally, okay, such that there is T1 and there is T2. Okay, now let us take the case where there is no friction. It means we can write F net equals, now it can be T1 minus T2 or T2 minus T1. Which do you think it should be? If we go by our sign convention, then it should be what? T1 minus T2. Why? Our T1 is moving forward, which means it's acting towards a positive x-axis, and then our T2 is moving backward, which means it's acting towards a negative x-axis. Now, if our T1 is greater than T2, it implies that the whole body of mass here would accelerate forward, alright? And as such, we can write MA equals T1 minus T2. But if our T2 is greater than T1, it implies that the whole system of mass would move towards the negative x-axis, and as such we would write minus MA equals T1 minus T2. Now, both our T2 and the system of mass are having negative signs. Why? Because they're moving towards the same direction, right? Which is our negative x-axis. Alright, now let us consider a case where there is frictional force, such that again our friction opposes motion. Okay, now if there is friction and our T1 is greater than T2, so let's say if our frictional force exists such that it is equal to mu mg, and we have that T1 is greater than T2, then we can write that our net force MA is equal to, we'll have T1 minus T2 and then minus frictional force. Why? Our frictional force would be acting in such a way as to oppose motion. Frictional force will be acting towards a backward direction. Alright? But if friction exists, but our T2 is greater than T1, in that case the whole system would move backward, right? And as such would have minus MA equals, our T1 is still positive because it's going forward, and then our T2 is still negative because it's going backward. However, our friction this time would be acting in the same direction as T1. Alright, don't forget we have said T2 is greater than T1. As such, the entire system moves backward. Alright, so friction would tend to oppose the motion and as such would move forward. So we would say plus frictional force. Alright, or plus mu mg. So this is the sign convention that we shall be making use of as we go on in this video. Now, let us go to our first question. We're told that two bodies of masses 3 kg and 2 kg respectively are connected by a light inextensible string which passes over a smooth pulley, and that both bodies hang vertically. Okay, and then we're told initially the 3 kg is 1.5 meters above the ground, and then we're told that if the system is released from rest, we're told to find 1. Its acceleration, 2. The tension of the string, and then 3. The time taken for the 3 kg block to hit the ground. Now this is a picture of what we have in front of us. So let us get into solving it. The first thing I would want to do here is to write the expression F net equals tension minus weight. Why? Our tension always seeks to take the body upward, while the weight always acts downward. Alright? Now, let us consider our 3 kg mass. So, for the 3 kg mass, it is obvious that our 3 kg mass has more weight than the 2 kg mass, and as such, it's going to cause the whole system to move downward. Okay, now since it moves downward, it means we'll have minus ma, so we'll have minus 3a, okay, is equal to our tension minus the weight. Of course, we said the weight is mg, right? So we'll have 3 times g. Okay, we can call this equation 1. Next, we consider the 2 kg mass. Consider the 2 kg mass. For the 2 kg mass, what do we have? Now, you can tell me the mass moves upward, right? So we'll have 2a equals, again, tension minus weight. Like I said, the weight is always negative because it seeks to pull the body downward. Alright? Now, how do we find a? Because the first thing there we're told is to find the acceleration. How do we find that? We have two simultaneous equations, or we have a simultaneous equation that has a pair of this equation 1 and equation 2. How do we eliminate t? We can subtract, which means if we say equation 2 minus equation 1, it gives us what? 2a minus 3a becomes 2a plus 3a, and that's 5a. That becomes equal to t minus t gives us 0, so t goes home, and then we'll have minus 2g minus 3g, so we'll have 5a equals minus 2g plus 3g. Okay, this is the same thing as g. Why? This means 3g minus 2g, okay, which means therefore that a is equal to g divided by 5. Now, if we take our g to be 9.8, it means we'll have a to be 9.8 over 5. If we punch our calculator, that would give us 1.96 meters per second squared. Alright? Now, let us go further and solve for the tension. To find the tension, don't forget we were told, or we obtained a certain equation, okay, we obtained two equations, 1 and 2. We can use any of them to obtain the tension. Let's use equation 1 now. So from equation 1, we have that if we make our tension the subject of the formula there, it means we would move our minus 3g from the right here to the left, and as such would have minus 3a. When we move this minus 3g, it becomes a plus, so we'll have plus 3g equals t, which implies that the tension therefore is equal to 3 into g minus a. So we have 3 into 9.8 minus 1.96. Alright, if you play with that, you would have 23.52 newtons. That's 23.52 newtons. Alright, so that's the tension on the string. Next, we're told to find the time taken for the 3 kg block to hit the ground. Now, what are the things we have? We're told it falls from rest. Here it says if the system is released from rest. Okay, which means its initial velocity is 0. Next, we have found its acceleration to be 1.96 meters per second squared. We're told it is at a distance of 1.5 meters above the ground. Okay, that's our distance. S is 1.5 meters. Okay, then we're told to find the time. Which equation of motion connects all these terms? Don't forget there are several equations of motion. We have V equals U plus AT. We have V squared equals U squared plus 2AS. We have S equals UT plus half AT squared. We have S equals U plus V, that's average velocity times time. So you look through all these and see the one which connects the things we have and the parameter that we need. Okay, and it looks like this is the one which connects them. Okay, so let us apply that. If we apply that, we can see that U is equal to 0, right? As such, the equation collapses into S equals half AT squared. Alright, so if we make the time the subject of the formula, the first step is to cross multiply. We'll have 2S equals AT squared. Next, we divide both sides by A, and then we'll find the square root of both sides. We'll have T equals the square root of 2S over A. Let's apply that. We'll have 2 times our S is 1.5 over our A is 1.96. As such, we'll find that the T, the time T, would be the square root of 2 times 1.5 over 1.96, and that would give us 1.24 seconds. Alright, so we have achieved all that was said before us for this question. Let's take another exercise. The question says 2 masses of 3 kg and 4 kg hang vertically and are connected by a light string with the 4 kg mass above the 3 kg mass. The 4 kg mass is attached to another string which passes over a smooth pulley and supports a third mass of 5 kg hanging vertically. We're told the system is released from rest. The question says find the tension in the string connecting the A 4 kg and 5 kg masses and B the 3 kg and the 4 kg masses. Alright, so I would call the tension between the 3 and the 4 kg mass, I would call that T2. So here we have T2, and then the tension between the 5 kg and the 4 kg, I would call that T1. Right now, since it is a smooth pulley, it implies that it is frictionless, and as such the tension here would be the same as the tension here. Alright, there is no lost force. So this is T1 and this is also T1. Alright, now let's go ahead and solve the problem. It means we're first solving for T1 before we solve for T2. Okay, so we write that our net force is equal to tension minus weight. Now, let us consider the 5 kg mass first. Which direction do you think it would go when the system is released from rest? Do you think it would go upward or downward? Take time to think about that. Now, on the left here we have 2 masses, 4 and 3 kg, of which the sum of that gives us 7. But on the right we have only 5 kg. It implies that the weight on the left would be more than that on the right, which means the system would fall towards the left. Okay, as such our 5 kg mass would move upward. Alright, since it's going upward, it implies it's moving towards the positive y-axis. Alright, so we'd write our net force with 5A. That becomes equal to the tension minus the weight of our 5 kg mass would be 5g, where of course g means acceleration due to gravity. We'll call that equation 1. If we consider the masses on the left, right, That's the 7 kg sum of masses. What would we have? Now we all know that the 7 kg weighs more, so it will fall downwards, right? So it goes in the negative y-axis. We'll write minus 7a equals the tension minus 7g. We call that equation 2. Okay, so let us eliminate t. We can do that by subtracting equation 2 from equation 1, which means we have 1 minus 2. And that would give us what? It gives us what? We have 5a minus 7a, which becomes 5a plus 7a, and that's 12a. That becomes equal to t minus t gives us 0, so t is gone. We'll have minus 5g minus 7g. Minus 5g minus 7g becomes minus 5g plus 7g, and that gives us 2g. Alright, and as such we'll have that a becomes 2g over 12. Now if we take our g to be 9.8, we would have 2 times 9.8 divided by 12. If we play with that, we have 9.8 over 6, which would give us 1.63 meters per second square. Alright, that is the acceleration of the system. Now, how do we get our T1 and T2? For us to get our T1, which we're solving for first, we can use either equation 1 or equation 2. Okay, let's use equation 1. From equation 1, if we make our T the subject of the formula, we'll have T becomes equal to, if our minus 5g move over to the left, we would have 5a plus 5g, which means we'll have 5 into a plus g, and as such we'll have 5 into, we found our a to be 1.63, and then our g is 9.8. Alright, if we play with this, 5 times 1.63 plus 9.8, if we punch our calculators, let's see what that would give us. Correct, that would give us 57.15 newtons. Alright, so that's our T1. Now, for us to get T2, how do we solve that one? We consider again the fact that our F net is equal to T minus W, and this time we focus on the 3 kg mass. Consider the 3 kg mass. If we consider that mass, now since the system is falling, since the system is falling towards the left, it implies our 3 kg mass is also falling, right? So we have minus 3a equals our tension now, which will be T2 minus the weight. Okay, so we have minus 3a equals T2 minus 3g, where of course g stands for acceleration due to gravity. Our T2 therefore becomes, again we'll move our minus 3g to the left. Alright, so we'll have minus 3a plus 3g, which means 3 into g minus a. Alright, please you pardon my dog, it's barking at the background, but let's go ahead, I'm sure it's fine. Okay, we'll have 3 into 9.8 minus 1.63. We play with that, and we have that the tension is equal to 24.51 newtons. 24.51 newtons. Alright, so we found the tension between the 4 and the 5 kg mass as T1, which is 57.15 newtons, and also we found that between the 3 and the 4 kg, and we found that as 24.51. So this is the practice question. Alright, we're told to find the acceleration of the system, alright, and then to find the tension which connects the 6 and the 4 kg masses, and that which connects the 5 and the 4 kg masses, which means T1 and T2. Alright, so I'll just go ahead and label one of them T1. So the first one between the 6 and the 5 kg masses, let's call that T1. Alright, so this is T1 and this is T2. Okay, and then lastly for the C part, it says find the time it takes the 5 kg mass to hit the ground if it was initially 2 meters above the ground. So go ahead and play with these questions, apply the principles you've learned from the previous questions we solved, and you should be home and dry with these answers. This question says a block of mass 4 kg rests on a smooth table 1.5 meters from the edge. It is connected by a light, inextensible string which passes over a pulley at the edge of the table to a second block of mass 3 kg hanging vertically over the edge. Next it says, initially the 3 kg mass is 1 meter above the ground. We are asked to find the acceleration of the system and also the tension on the string and then the speed v with which the 3 kg block hits the ground when the system is released from rest. This is a diagram which depicts the question we are going to solve. Okay, so let us again wave our magic wand at the question, and the magic wand is that F net, our net force, is equal to tension minus weight. Alright, now let us consider the 3 kg mass. Consider the 3 kg mass. Now for this mass, where do you think it would go, downward or upward? Definitely it's going down. Alright, so that's towards the negative y-axis. We'll write minus 3a, that becomes equal to T, the tension T there, minus the weight, which is 3g. Okay, from this equation, let us make T the subject of the formula. We'll have T becomes equal to, when our minus 3 moves over to the left, we'll have 3g minus 3a. We can call this equation 1. Alright, now let us consider the 4 kg mass. Alright, now for this mass, don't forget we studied the case of horizontal of a body that lies on a horizontal surface. There is no frictional force acting on it here, so we can simply write that the net force is simply equal to the tension. Alright, it implies that 4a therefore is equal to T. Okay, we'll call this equation 2. Now this tension here is the same as this tension here, so we can equate both equations. Alright, so equating 1 with 2, alright, it implies that we have 3g minus 3a being equal to 4a. If we collect like terms here, we'll have 3g equals 4a plus 3a, which gives us 7a, and therefore we'll have that a equals 3g over 7. If our g is taken to be 9.8, we'll have 3 times 9.8 over 7, and that would give us 3 times 9.8 over 7. Let's punch that, and we would have 3 times 9.8 over 7 gives us 4.2 meters per second squared. Alright, 4.2 meters per second squared. That is the acceleration of the system. Next, we're told to find the tension on the string. Okay, now let us use equation 2. From equation 2, we have that the tension is equal to the 4 times acceleration, c equals 4a, which means 4 times 4.2, and that should give us 16.8 newtons. Alright, that's the tension. Next, we're told to find the speed with which the 3 kg block hits the ground when the system is released. Now, what are the quantities we have here? We're told to find speed, it's unknown. We have acceleration to be 4.2 meters per second squared, and then we're told it is released. Alright, from rest. So that implies that u is equal to 0. Okay, and then we also are told that it is 1 meter above the ground. Okay, which means s is 1 meter. Which equation links all these? From the equation we wrote, from the set of equations we wrote earlier, we would find out that the most ideal one to use is v squared equals u squared plus 2as. Again, our u is 0 because the system is released from rest. As such, the speed becomes the square root of 2as. Alright, so we have the square root of 2 times 4.2 times 1. Alright, you play with that, you have the square root of 8.4, and that should give us the square root of 8.4. That gives us 2.898 meters per second. Alright, so that is the speed with which the 3 kg block hits the ground when the system is released from rest. Let's go on to this one. It says the table in the question above was changed to one with a rough surface having a coefficient of friction mu equals 0.2. We're told to obtain again the values of A, T, and V. Alright, so this is the diagram. Let us play with this. Again, we wave a magic wand at it, which is that the net force equals tension minus weight. Alright, again, let us consider. Now, if we consider our 3 kg mass, we would have exactly the same formula as we had before. Why? Because friction does not affect our 3 kg mass. Alright, which means we can still write minus 3a equals t minus 3g as our equation 1. Alright, now when we consider the 4 kg mass, in this case friction would have a role to play. Why? Friction opposes the motion of the body. Our net force therefore is going to be equal to tension acts forward while friction acts backward to oppose the motion. Alright, so we have net force equals T minus FF, but our net force of course is MA. Alright, and then we have established earlier that our frictional force is mu N or mu mg. Alright, now this is mu here. Okay, mu mg, where mu means the coefficient of friction, m is the mass, and g is acceleration due to gravity. So let us apply that here. Our net force is ma, so we have 4a is equal to t minus mu, which is 0.2 times 4 times 9.8. Let's just write g for now. Okay, so we have 4a equals t minus 0.8 g. We call that equation 2. Okay, now let us solve this simultaneously. Alright, that is equation 1 and equation 2. Let us solve them simultaneously. How? Let us subtract 1 from 2. Okay, we have 2 minus 1 gives us what? We have 4a minus 3a, which becomes 4a plus 3a, and that's 7a becomes equal to t minus t gives us 0. Then we have minus 0.8g minus 3g, alright, which becomes 3 minus 0.8, right? That's 3g minus 0.8g, and that gives us 2.2g, and therefore a becomes equal to 2.2g over 7. That becomes 2.2 into, let's take our g to be 9.8 over 7. If we play with that, 2.2 times 9.8 over 7 gives us what? 3.08 meters per second squared. 3.08 meters per second squared. So we can see here that the system has a lower acceleration than it did before. Okay, and then to find the tension, would have, let us use this equation 1, alright? Could as well have also used equation 2. Anyone can be used. So we say from equation 1, we have the tension is equal to, again we'll move our 3g to the left to collect like terms. So we'll have 3g minus 3a, alright? That becomes 3 into g, which is 9.8, minus a, which we found to be 3.08. Alright, if we do that, 20.16 newtons. Alright, 20.16 newton. Alright, so that is the tension. Next it says find the speed. Again, we use the equation v squared equals u squared plus 2as. Alright, as such, we know that it starts from rest, so u is 0. We have v therefore becomes equal to the square root of 2as, which becomes the square root of 2 times, we found a here to be 3.08, and then times the distance it falls through is 1 meter. If we play with that, we have square root of 6.16, and that would give us 2.48 meters per second. Alright, let's move over to some other questions. Here we're told a block of mass 1 kg rests on a smooth table. It is connected by a light inextensible string passing over a smooth pulley at the edge of the table to a second block of mass M2 hanging vertically over the edge of the table. Next, we're told that when the system is released from rest, the tension in the string is 48 newtons and the system moves with an acceleration of 4 meters per second square. We're told to find the values of M1 and M2, and then also we're told to find the force on the pulley. Alright, let's play with this question. Here we have, this is the diagram of the question. We have F net equals T minus W. Now, let's consider the mass M2. Considering mass M2, what can we write about it? Our M2 mass, as well know, would fall downwards. So we can write minus M2A is equal to T minus M2G. Now, our A, we are told that the value of A is 4 and the value of T is 48. So we have minus 4 M2 equals 48 minus M2G. Alright? So with this we can easily find our M2. Alright? Now our G here is 9.8. So we have minus 4 M2 equals 48 minus 9.8 M2. Let us collect like terms. If we move 9.8 M2 to the left, it becomes a positive value there. We have 9.8 M2 minus 4 M2 equals 48. And this would give us 9.8 minus 4 should give us 5.8. So we have 5.8 M2 equals 48. And therefore, M2 is 48 over 5.8. You punch that, we would have what? 8.276. Alright? 8.276 kilograms. Okay? Next, we're told to find M1. Okay? Now, if we consider mass M1, what do we have? We have that the net force is equal to the tension on the string, okay? Although the tension is not shown on the diagram, but we know we can as well put the tension there. If we desire that, we can write tension here and tension here. Alright, still the same thing. So let's apply that now. we have that the net force is simply equal to the tension. Why? There is no frictional force acting against it. Okay, so we have M1A equals T. Okay, now we're told that A is 4, so we have 4 M1 equals, we're told that T is 48, so we have 48, and therefore M1 equals 48 over 4, and that gives us 12 kg. Lastly, we are told to find the force on the pulley. Now here we have two masses that are perpendicular to each other. Alright, now how do we find the force? We understand that each of the masses have a tension T. Okay, so there is a tension T from mass M1. Okay, that's tension T. There's also a tension T acting upward from mass M2. Okay, our pulley lies somewhere here, and as such, the net force will be in this direction. Let's call it F, the force on the pulley. Okay, how do we find this force? We apply the triangle law of forces. We try to make a triangle out of the forces such that this T up here, the horizontal T, can also be drawn as this. Okay, so this is the same thing as this T here, and as such I will have a right angle triangle such that two sides are known. The value of T was given to us here as 48 newtons, the same as this T, alright, because they're both the same thing, alright. They both stand for the tension. How then do we find F? We simply apply the Pythagoras theory, which tells us that the square of the hypotenuse is equal to the sum of the square of the two other sides of a right angle triangle. So we have F squared equals T squared plus T squared, which means F squared equals 2T squared, and as such F is the square root of 2T squared, which means the square root of 2 times 48 squared, and that gives us 67.88 newtons. Alright? Practice questions to play with. Okay? You could look at them. They're very simple. I believe you'll be able to get them if you look at the steps we have used for the previous questions. Okay, and this is what you should obtain. The first question A there is the case where we assume that there is no frictional force, and then the second part there, that's the B part, is the part which takes into consideration the frictional force such that the coefficient of friction between the 3 kg block and the table is 0.2. Alright, so play with that and you should obtain the values displayed as the answer. The last part of this video will have sets of questions, just 3 questions that look interesting. Okay, so here we have two masses connected together, 3 and 4 kg masses lying on a horizontal table, and then a 5 kg mass which hangs freely. We're told to find the tension in the string that connects the 5 and the 4 kg masses, and then to find the tension that connects the 3 and the 4 kg masses. I'll label my T1 and T2, so permit me to change my pen here to black, and then I'll call this T1. This is also T1 because we assume that the pulley is smooth and that it is frictionless, and then we'll call this T2. So how do we solve the question? Again, we write net force equals tension minus weight. If we consider the 5 kg mass, we're told it moves downward, alright, which implies we can write minus 5A equals the tension minus the weight, which will be 5G, which is 5G. Alright, now since it's for T1 we're solving, let us make it the subject of the formula. We'll have T1 equals, this becomes 5G minus 5A. We call that equation 1. Alright, now we look at the system of masses which are lying on the horizontal table. If we put those masses together, it gives us 7 kg. So we say consider the 7 kg sum of masses. Alright, if we do that, we'll have our net force is simply equal to T1, because we're summing our 3 and our 4, and as such we cannot observe T2, which lies between 3 and 4 kg masses. Alright, so we can just simply write that MA, in this case we can write 7A, alright, equals our T1. We can call that equation 2. Alright, now we can equate 1 and 2 because they're both expressions of T1. Okay, which means we'll have 5G minus 5A equals 7A. Alright, if we play with that, it becomes 5G. Now let us collect like terms. 5G equals 7A plus 5A, which gives us, okay, let me just write it out first, 7A plus 5A, which is 12A, which implies that A is equal to 5G over 12. Now since our G is 9.8, we have 5 times 9.8 over 12, and that gives us what? 5 times 9.8 over 12, you punch your calculator, and that gives you 4.083 meters per second squared. 4.083 meters per second squared. However, that is not what they've asked us to find. They've asked us to find T1 and T2. So let's do that. First of all, for T1, we use the equation 2. Okay, it's easy to find it from equation 2. From equation 2, we have that T1 equals 7A. Alright, which means 7 times 4.083, and that gives us 28.583 newtons. 583 newtons. Alright, now how do we find our T2? We consider the 3 kg mass. Consider the 3 kg mass. If we do that, we'll have the net force on that mass is equal to T2 only. Alright, T2 is the tension which has a direct contact with the mass 3 kg, and as such it's the only force that is exerted on the 3 kg mass. There is no frictional force. Alright, so we're stuck with this. So we'll have the 3 kg mass moves forward, and as such we can write 3A equals T2. Okay, the net force on our 3 kg mass is MA. Alright, that's 3A. Okay, equals T2, which implies therefore that T2 is simply 3 times 4.083, and that gives us 12.25 newtons. Next question says 2 masses 3 and 5 kg are hanging. Now this is a question, we have it in front of us. Let's just go straight. It says the system is released from rest such that the 5 kg mass moves downward. Okay, this pattern that moves downward. Okay, then the question says find the tension in the string which connects the 3 kg and the 4 kg masses, and then the 5 kg and the 2 kg mass. So I'll call them, let me label them T. I'll call this one T5. Okay, that's the tension due to the 5 kg mass. I'll call that T5, and then I'll call this one, this is still T5. Okay, while this, I'll call this T3 and this T3. Okay, so let us go ahead to solve this. Let's have some fun with this. I'll change my pen to a white one, and then let the fun begin. We'll have that the net force is equal to tension minus weight. That's our magic wand. Okay, let us consider the 5 kg mass. Consider the 5 kg mass. If we do so, what do we have? We have that we're told it moves downward, right? So we can write minus 5A equals T minus 5G. that is equation 1. Okay, or let us rearrange this to have T equals 5G minus 5A. Alright, this is still equation 1. We just rearranged it. Now let us consider, now don't forget this is for T5. Okay, now let us consider the 3 kg mass. For this one, we're going to have, now it's going upward, so we write 3A equals T3 minus 3G. Alright, which implies that T3 is equal to 3A plus 3G. We can call this equation 2. Next, we consider the 4 kg mass. We consider the 4 kilograms mass. If we do that, we'll observe that our net force, the net force on it, that's MA, okay, let me just write that's net force, is going to be equal to T5, which moves forward, minus T3, which moves backward. Okay, which means we have 4A equals T5 minus T3. We call that equation 3. Okay, the next thing for us to do is to substitute equations 1 and 2 into equation 3, which implies that equation 3 becomes 4A equals, in place of our T5 from equation 1 we have 5G minus 5A, and then minus, in place of T3 we have 3A plus 3G. So this gives us 5G minus 3G. Okay, let me just open up the bracket first. We have 5G minus 5A minus 3A minus 3G. Alright, so 5G minus 5A gives us, 5G minus 3G gives us 2G, and then minus 5A minus 3A gives us minus 8A. So we have 4A equals 2G minus 8A. We collect like terms, we'll have 4A plus 8A, and that gives us 12A equals 2G, which implies that A equals 2G over 12. Now if our G is 9.8, we'll have 2 times 9.8 over 12, and this gives us 1.63. So we have that A therefore is equal to 1.63 meters per second squared. So how do we get our T5 and our T3? For T5 we simply use equation 1. So we have from equation 1 our T5 is equal to 5G, which means 5 times 9.8, and then minus 5A, that's 5 times 1.63. We play with that, and that should give us 40.85 newtons. Alright, 40.85 newtons. And then how about our T3? We obtain that from equation 2. From equation 2 we have that our T3 is equal to 3A, that's 3 times 1.63, plus 3G, that's 3 times 9.8. Alright, we'll play with that. We would have 34.29. 34.29 newtons. Alright, so we have been able to obtain the values of T1, of T3 and of T5. If you've made it this far in this video, you have done well. We are told the table in the question Q7 above was changed to one that has a rough surface such that the coefficient of friction between the table and the 4 kg mass is 0.2. We're told to obtain the values of T3 and T5. Okay, I'll label them again, T3 and T5, such that we said this here is our T5, while this is our T3. Okay, now we're told the table is now one that has friction. Okay, so it means The only equation that would change is our third equation, equation 3. Don't forget we said for the first equation, I'll just go ahead and write them out. Okay, for the first equation we said we have recall f net equals t minus w. As such, we have minus 5a equals, and then we had t minus 5g, which gave us t5 to be equal to 5g minus 5a. That was our equation 1. That was the first equation. Then for the second one, we had 3a equals t3 minus 3g, and that gave us t3 equals 3g plus 3a. Alright, to call that equation 2. So the only equation that will change is the equation for our 4 kg mass. Alright, so considering the 4 kg mass, what are we going to have? We'll have that the net force is equal to, we have T5, which pushes it forward, and then minus T3, which acts backward, and then minus the frictional force, FF. Alright? But we know that our frictional force equals mu mg for a body that lies on a horizontal surface. Alright? Mu mg, where of course mu is the coefficient of friction, which was given to us as 0.2. Okay? It means we can write that 4a equals T5, then minus T3 minus mu, which is 0.2, times m, which is 4, times g. So we have 4a equals T5 minus T3 minus 0.8g. Alright, we call that equation 3. Now, we substitute our first and our second equations into equation 3. Okay, as such, we have that 4a is equal to, in place of T5, we can write 5g minus 5a, and then minus, in place of T3, we can write 3g plus 3a, and then minus 0.8g. Okay, so together we have 4a equals 5g minus 5a minus 3g minus 3a minus 0.8g. If we collect like terms, we have minus 5 minus 3, that's minus 8. If they move over to the left hand side of this equation, we would have minus 8 moving over becomes just 8. So we have 8a plus 4a, and that is 12a, equals 5 minus 3, that's 2g. Alright, and then 2 minus 0.8 gives us 1.2. Okay, let's say that again. 5 minus 3 is 2, and then 2 minus 0.8 is 1.2. So we have 1.2g. Alright, if we play with that, we would have that a therefore is equal to 1.2g over 12, and that becomes 1.2 times 9.8 over 12. Alright, if we do that, we would have 11.76 over 12, which implies that a is equal to 0.98 meters per second squared. Alright, so to get our T5, we just use our first equation there, equation 1. From equation 1, our T5 is equal to 5 into 9.8 minus 5 into 0.98, and together that gives us 44.1 Newton. Alright, 44.1 newtons. Now, from equation 2, we have that our T3 is equal to 3 into 9.8 minus 3 into 0.98. Okay, if we play with that, we have that our T3 is equal to 32.34 newtons. 32.34 newtons. Alright, so we have been able to answer the question that was given to us to solve. Next, we have a set of practice questions for you to play with. Okay, this is the question. Read it through and play with it. You should have this as your answer. Here we called our T2 the tension between the 2 kg and the 4 kg. So this here is what is being referred to as T2, while this is T7. Alright, if you play with this, you should have the answers that are given. If you're able to get these answers, it's a clear evidence that you have been able to clearly understand the concepts that was taught in this video. Alright, our next video shall be one where we'll look at inclined planes. Alright, we'll have questions that would look like this, where we have mass here, we have a mass here, they're connected by a pulley. Alright, they're connected by a pulley, and then we'll have one sliding such that there's an angle here, theta. Okay, we'll play with questions like this. We'll also solve a case like this as well. So it promises to be a very interesting class. So if you've enjoyed this video and you look forward to that one, please subscribe to this channel. Alright, like the video, share it, and if you have questions, difficulties, contributions, please let me know on the comments section. Alright, thanks for watching and see you in our next video.